Namaste everyone, welcome to Vidya Lakshmi School YouTube channel. Myself Moses, chemistry teacher here. In this video, I am going to discuss haloalkanes and haloarenes in one chat. Okay, let us see what we can discuss in this video. Okay, the first thing what we can discuss here is nature of bonding between carbon and halogen. Because if you take haloalkanes and haloarenes, right, the common bonding is what? There is a bonding between what? Carbon and halogen over there, right? And the second one is preparation of haloalkanes and haloarenes. Okay. Third one is physical properties. Fourth one is chemical properties. Right. If you take any organic chapters, right, first we will have a introduction, IUPAC nomenclature, and preparation, physical properties and chemical properties. This is what the trends we have to follow for the particular chapter. Okay. Next, let us go with the nature of CX bond over there. Okay. If you take haloalkanes or haloarenes, right, the common thing which we can see is that the CX bond over there. Okay, the X might be any halogen, X might be fluorine, chlorine, bromine, iodine. Okay, for example, if you take a carbon and halogen bond over there, what happens here is that we should remember one thing about the electronegativity of carbon and halogen, right? Halogens will have more electronegativity comparatively with carbon over there, because of which the shared pair shifting takes place towards the halogen, because of which halogen gets partial negative charge, carbon gets the partial positive charge. Okay, what is this? Since halogen atoms are more electronegative than carbon, the carbon halogen bonds are alkyl, like what I can say, of alkyl halides is polarized. It's due to what? It is due to what? Electronegativity difference over there, electronegative difference. Okay, now let us take the bond length over there. Okay, if you take like all the halogens, right, from top to bottom, fluorine, chlorine, bromine, iodine, right, what happens is that the atomic size increases. As atomic size increases, atomic radius increases. As atomic radius increases, bond length also increases. Okay, if you take the bond length order, right, if you take RF, RCl, RBr and Ri, okay, alkyl, fluoride, chloride, bromine, iodine. Okay, as we go like from top to bottom, right, atomic size increases, bond length also increases over there. That's what the bond length order is going to be, this one. Bond length order is going to be this one. Okay, now when it comes to bond enthalpies, right, bond enthalpies are nothing but we can simply say it is as the amount of energy required to break 1 mole of bond over there, right. Simply we will call this one as the bond strength. Okay, as we go from top to bottom, what is happening to the bond length? Bond length is increasing, right? As bond length increases, it is easy to break it, right? Similarly over here, as bond length increases from top to bottom, like the Ri which is there, alkyl iodide, is required less amount of temperature or less amount of energy to break the bond over there, because of which the Ri or methyl iodide has the least bond enthalpy. The least bond enthalpy. Okay, since RF has the shortest bond, okay, the least bond length, because of which it has more bond enthalpy. It has more bond enthalpy over there. Okay, simply we'll just remember it as bond length is inversely proportional to bond strength or bond enthalpy or bond energy also we can call. Okay, now there is no particular order in the case of dipole moment. You just remember something like this. Okay, we have chlorines first. Alkyl chlorines will have more what I can say dipole moment, followed by alkyl fluoride, followed by alkyl iodide, followed by alkyl bromide. Okay, first chlorides, followed by fluorides, followed by iodides, followed by bromides. Okay, this is the order of dipole moment. Okay, this is about the nature of CX bond and the different trends in the with respect to bonds over there. Okay, let us go with some other things. Okay, select the correct order of dipole moment for the alkyl halides. Right, now only we have discussed first chlorides, followed by fluorides, followed by iodides and bromides over there. Okay, where do we have first chlorines? We have in the case of B, right? In the case of first one we have iodides, and in the case of third one we have fluorides over there. In the case of option B only we have fluorides, right? Sorry, chlorides, fluorides, bromides and iodides. This is the answer as per the experimental data given in the textbook. Okay, next let us go with the preparation methods of haloalkanes and haloarenes. Right, now let us go with the first preparation method, that is from alcohols. Okay, now if you take all these reactants, right, all these reactants has a group called OH group, right. This group is nothing but what? Alcoholic functional group. This group is nothing but what? Alcoholic functional group. Okay, now just like from alcohols, in the sense what we have to remember is that this alcohol group ROH group should be converted into RX group. This alcohol group should be converted into what? RX group. Means here the bond between RO means CO bond is breaking, a new bond between CX is forming. Okay, to the carbon where oxygen is connected, there is a new bond formation is taking place between carbon and halogen over there. Okay, now to happen this one, right, what is the new like atom came over here? We have halogen over there, right? Halogen in the sense what I can say, we need a kind of reagent which donates the halogen atoms, right? Now we have all these reagents, right? All these reagents are what? Halogenating reagents. All these atoms are what? Like reagents are what? Halogenating reagents. Okay. Let us see the first preparation method is from alcohols. Okay, alcohols. Okay. Now alcohols means what? If you take all these reactants, right? All these reactants have one thing in common, that is OH group. Okay. OH group is the functional group for alcohols actually. Okay. Now this ROH group should be converted into RX, which means this RO bond should be broken. A new bond between alkyl group and halogen group should be formed over there, right? To get halogen over there, we should need certain reagents which we are calling here it as halogenating reagents. Okay, all these reagents which we have used for the preparation of alkyl halide from alcohols are what I can say, halogenating reagents over there. Okay, one thing we have to remember here, like RO bond is being broken here, a new bond between RCl is being formed over there. Okay, let us see the first reaction. Okay, the first reaction what we are using is that we are using the combination of ZnCl2 and concentrated HCl. Okay, this combination is known as Leucas reagent. Okay, now we can prepare alkyl halide from alcohol by using Leucas reagent. Okay, the importance of this Leucas reagent is it can be used for the identification of alcohols. Okay, now how can we identify the alcohols over there? In the sense, based on the reactivity of alcohols. Okay, now if you take primary, secondary, tertiary alcohols, right, the tertiary alcohols are more reactive towards Leucas reagent, followed by secondary, followed by primary. Okay, the one which gives a immediate turbidity, right, that is tertiary, like after 1 or 2 minutes, right, secondary alcohols will give. Tertiary like primary alcohols takes much time over there. Okay, and if you take, right, like for primary and secondary alcohols, right, they are required some amount of temperature to react with Leucas reagent, but not tertiary alcohols. Okay, tertiary alcohol can react with alcohols at room temperature. Okay, second one is another combination is sodium halide with H2SO4, simple substitution reaction takes place, right, and third one is with PX3. Okay, if you take PCl3 phosphorus trichloride, right, we'll get 3 moles of alkyl halides over there. Okay, now the ratio between the reactivity of alcohols and PCl3 is going to be 3 moles of alcohols ROH plus 1 mole of PCl3, means 3 replaceable chlorines are there. Those chlorines can be attached with what? Alkyl group and forms alkyl halides over there. Okay, the third one is fourth one is PCl5 phosphorus pentachloride, and the fifth one is a good reducing agent. What is this one? Red phosphorus with a halogen over here. Okay, and the last one is SOCl2, which is known as phenyl chloride, which is one of the good preferable reagent for the preparation of alkyl halides. Okay, why it is like good preferable reagent? In the sense, by using thionyl chloride we can prepare alkyl halide. Along with that we will get certain byproducts over there, right? These two byproducts are gases. What? Gases. Okay, gases can easily be escapable over there. When gases like escapes from the particular reaction mixture, we will get pure alkyl halides over there. And according to Le-Chatelier principle, when this byproducts gets like out of the reaction mixture, right, what happens? Concentration of the product decreases, equilibrium shifts in a direction to increase the concentration of product, by which we can increase the production of alkyl halides. Okay, these two reagent things we have to remember in terms of SOCl2. Why SOCl2 is more preferable reagent? In the sense, what we have to say, the byproducts are gases, can easily escapable. According to Le-Chatelier principle, what happens? By escaping the gases over there, concentration of the product decreases, like equilibrium shifts in a direction to increase the concentration of products over there. Okay, these are the two reasons why thionyl chlorides is preferable reagent over all these halogenating reagents for the preparation of alkyl halides from alcohols. Okay, next let us see the decreasing order of reactivity, okay, in these reactions. Okay, how we can say, like, which is going to be, like, what I can say, more reactive actually. Okay, now what do we have? We have all alkyl like hydrogen halides, right? Let us take hydrogen fluoride, hydrogen chloride, hydrogen bromide and hydrogen iodide, sorry, hydrogen iodide here, okay, hydrogen iodide, bromide and iodide, okay. Now let us take 1, 2, 3 and 4, okay. As we go from top to bottom, right, we have already discussed about the bond length, okay. From top to bottom, fluorine to iodine, atomic size increases, bond length increases, okay. What is the bond length order? Bond length order is what? Bond length order is 4 is greater than, 3 is greater than, 2 is greater than 1. Okay, what about the bond strength? What about the bond strength? 1 is greater than, 1 is greater than, 3 is greater than, 2 is greater than 1. Now, this reaction, okay, depends on the strength of the HX bond over there, HX bond over there. In which case, like this HX bond can easily be broken, okay, that depends over there, okay. Now, sorry, what do we have here is that first one is greater than, bond strength, when it comes to bond strength, it is first one is greater than, second one is greater than, third one is greater than, fourth one, right? Which has the least bond strength here? The fourth one, because of the more bond length, right? It has less bond strength over there, by which this bond can easily be broken over there. And what happens here? It forms I minus plus H plus easily, H plus easily over there, because of which it is a good incoming nucleophile, good incoming nucleophile over there, because of which we can expect this order. Which order? The bond length order. What is this one? 4 greater than, 3 greater than, 2 greater than 1. This is the like what I can say decreasing, like what I can say increasing order of bond strength, right? Now in which case we have least bond strength actually. In the case of iodine we have easily iodine comes out over there, followed by bromine, chlorine and fluorine, right? That's why the answer is going to be what? 1. Answer is going to be what? 1. Let us go with another type of reaction, preparation of alkyl halides by free radical halogenation reactions, right? Now for example, let us take an alkane. Let us take a butane, that is CH3, CH2, CH2 and CH3. We have butane over here, right? Now butane means we have 4 carbons, all are connected with a single bonds over there, right? Generally this is a saturated hydrocarbons because we don't have any kind of double bonds or triple bonds right now, okay? Now what I would like to mention here is that simple hydrocarbons, like saturated hydrocarbons, are least reactive towards any kind of reactions because of the electronegativity difference between carbon and hydrogen is very less, right? Now this will undergo reaction in extreme conditions. It means when we apply more amount of energy in terms of light or heat, right, they can readily undergo reaction over there. This can undergo free radical substitution reaction in presence of light. We will take it as UV light, or in presence of heating conditions, okay. They'll react with chlorine, and gives what? Monochloro products over there. Now what I would like to ask you here is that, now how many products are possible here? How many products are possible over there? It depends on types of hydrogens over there, okay. Now if we take both the terminal carbons over there, these two terminal carbons are primary carbons, because this carbon is connected to one carbon, this carbon also is connected to what? One carbon. The hydrogens which are connected to the primary carbons are going to be what? Primary hydrogens, okay. Now if you take third and fourth, like second and third carbons over there, these two are secondary carbons. Why these two are secondary carbons? Means this carbon is connected to 2 carbons, this carbon is also connected to 2 more carbons over there, right? These two are secondary carbons. The hydrogens which are connected to the secondary carbons are going to be what? Secondary hydrogens, right? Now since we have only 2 types of hydrogens, right, we can expect 2 kinds of products over there, 2 kinds of products, okay. One is like what I can say primary chlorobutane, second one is what? Secondary chlorobutane over there, okay. Let us take the first product, where chlorine can replace what? Primary hydrogens, right? Let us take the butane over there, CH3, CH2, CH2, and finally we have CH3, right? One of the hydrogen is being replaced with what? Chlorine. That's what we'll get CH2 and Cl. There is one where a primary chlorine chloro product formation takes place, and the second one is what? Secondary hydrogens being replaced over there, right? What is this one? CH3, CH2. Let me take it as CH and CH3. At the secondary carbon, right, one of the hydrogen is replaced over there, and what we'll get? We'll get secondary chloro product over there, secondary chloro product, okay. This is what by free radical halogenation reaction. This is an example for free radical substitution reaction, Why it is substitution reaction? Now from chlorine, right, chlorine free radical generation takes place. This chlorine free radical replaces what? Or substitutes what? Hydrogen over there. Here we have 3 hydrogens, right? One of the hydrogen is being substituted with what? Chlorine radical over there, chlorine radical. Next, okay, Let us see here, identify all possible monochloro structural isomers expected to be formed on the free radical monochlorination of isobutane, isopentane it is given. Okay, let me take it here. Okay, what is this one? We have CH3, okay, CH3, CH2 and CH3. Okay, how can we identify how many monochloro isomers are possible with this one, right? Now let us identify what kind of hydrogens are there here. Okay, we have a primary hydrogens. Here also we have primary hydrogens. Here also we have primary hydrogens. Okay, but these two are identical. Because these two are connected with the same carbon over there, and we have a tertiary hydrogen and we have a secondary hydrogens. Okay, now these together one monochloro product. This is one, like here one substitution takes place, here also one and here also one, right? Altogether how many are possible actually? 1, 2, 3 and 4. Now you may get a doubt, right? Like we have 3 monochloro, like what I can say primary hydrogens over there, 3 together of same kind, right? But here the small difference is this primary hydrogen is connected to secondary carbon, these primary carbons are connected to what? Tertiary carbons over there, right? Let us take all those possible isomers over there. Let us go with the primary one. The first one is what? Primary substitution. Okay, let me take all these things here. Let me go with this primary substitution. CH3, CH3, CH2. This hydrogen being replaced over there. What happens? CH2, Cl will be formed. Okay, let us take another primary one. Out of these two, any one of this hydrogen can be replaced over here. Let me take it as CH2, Cl, single bond, CH3, single bond, CH2 and CH3. Let us go with secondary one. Okay, where do we have the secondary carbon? We have secondary carbon over here, right? This hydrogen will be replaced over there. Okay, what we'll get here? CH3, CH3, Cl and CH3. And what is the fourth one actually? This is the second, what I can get, secondary, primary one, third one and the fourth one. Okay, fourth one, what do we have? And remaining is the tertiary carbon is there where substitution takes place, and we'll get tertiary chloro product CH3, Cl will come and remaining CH2 and CH3 are going to be the same thing. Okay, altogether how many like what I can say monochloro products are we are going to get here? 4, because we have 4 types of hydrogens, right? 2 what I can say 2 identical primaries are there, another one is different primary is there because one is connected to secondary and 2 primary carbons are connected to the what I can say tertiary carbon over there. Okay, let us go the preparation of haloalkanes from alkenes. Okay, alkenes means what? We know that simple hydrocarbons connected with at least one double bond, right? For example, let us take C double bond C. Okay, let us take an what ideal alkene over there. Let me take an addition of hydrogen halide. Okay, simple like addition of hydrogen halide to the unsymmetrical alkene follows Marconico rule. Let me write what happens in the addition reactions. What happens? Double bond becomes single bond over there. Double bond becomes single bond. Okay, this double bond has turned into what? Single bond in the addition reaction. And addition of hydrogen halide takes place. Okay, let me take hydrogen here and halogen here. Okay, let us take an example. Okay, and let us take an unsymmetrical alkene. Okay, let us take a propene. Let us take CH3, CH, double bond, CH2. Okay, we have taken a propene right here. Okay, in this propene, what happens by the addition of hydrogen halide over there? Hydrogen halide. Okay, we know this addition of hydrogen halide to the alkene follows what? Especially unsymmetrical alkene follows what? Marconico rule. Okay, Marconico rule. Okay, what is this Marconico rule actually? This Marconico rule says that the negative part of the reagent goes to the carbon with less number of hydrogens. Okay, if you take these 2 carbons now. These 2 carbons over there, okay? We have first carbon and the second carbon, right? Second carbon has only one hydrogen, right? That's what we are calling this one as least number of hydrogen containing carbon, okay? The negative part goes to the carbon with least number of hydrogens over there. Least number of hydrogen over there. And then what is the product according to the Marconico rule over there? We'll get CH3, CH, double bond becomes single bond in the addition reaction, right? CH2. Then what do we have actually? Addition of hydrogen halide is taking place, right? This halogen goes to the carbon with less number of hydrogen. That's what X comes here and hydrogen comes over there. That is why this is the product over there. Okay. Now we have to remember one more thing. Okay. When we take unsymmetrical alkenes here, for example, let us take propene again. CH3, CH, double bond, CH2. Whenever addition of hydrogen bromide, HBr, hydrogen bromide in combination with peroxide, okay, any peroxide, okay, it will shows a peroxide effect, which is also known as anti-Marconico rule, okay. Now, in the case of Marconico rule, what we said, the negative part of the reagent goes to the carbon with less number of hydrogens, right? But in the case of anti-Marconico rule, right, in this combination alone, HBr and peroxide combination alone, it follows the anti-Marconico rule. The negative part of the reagent goes to the carbon with not less number of hydrogen containing carbon, but the carbon with more number of hydrogen, right? If you take 1 and 2, right, first one has 2 hydrogens and second one has 1 hydrogen over there. Since first one has more number of hydrogen, the bromine goes to the carbon with more number of hydrogen here, right? Then what happens here? We'll get a product, that is CH3, CH. We know that in the addition reaction, the double bond becomes single bond, that is CH2. And what do we have here? We have bromine and hydrogen, right? Bromine comes to the carbon with more number of hydrogen, and hydrogen goes to the carbon with less number of hydrogen, right? This is according to what rule? Anti-Marconico rule. Where the anti-Marconico rule we can see in this combination only. One is HBr and peroxide combination with unsymmetrical alkene. If it is symmetrical alkenes, we cannot follow any one of the rules because the adjacent carbons will have identical hydrogens over there. That is why we cannot say we cannot apply the Marconico rule or anti-Marconico rule to the symmetrical alkenes. Okay. Next, write the products of the following reactions over there. Okay. Now we have a simple reaction. Okay. Don't get confused here. Okay. There is no addition takes place in the benzene ring. Okay. But addition reaction takes place in simple alkenes. Now we have HBr, right? HBr means don't get confused. Okay. HBr with peroxide we have to follow anti-Marconico rule. HBr with alkene follows what? Marconico rule. Okay. Now if you take first and second carbon here, the second carbon has only one hydrogen, right? That's why the negative part goes to the carbon with less number of hydrogen. Okay. Let me take the first product here. The first product is going to be benzene. Okay, benzene. And what do we have here? Double bond becomes single bond over there, right? We have already one hydrogen. And what will comes? Let me write it over there. Okay, hydrogen and hydrogen. Okay. Now bromine goes to the carbon with less number of hydrogens, right? Here bromine will come. Here what will come here? The remaining part of the reagent, that is hydrogen. Okay. This is the product for the first reaction. Let us go with the second reaction. Here. Now what do we have? Again we have hydrogen halide. Okay. HCl will not follow any kind of anti-Marconico rule. Always gives what? Marconico product over there. Okay. We have a butane over there. It is an unsymmetrical alkene. Now what do we have again? We have a double bond, right? Which carbon has less number of hydrogen? This carbon has less number of hydrogen. That's what the negative part, that is chlorine, goes to the carbon with less number of hydrogen. Let me write the product here. That is CH3, CH2, single bond, CH, single bond, CH2. We know in the addition reaction double bond becomes what? Single bond. And where the chlorine will come, the negative part comes over there, carbon with less number of hydrogen. The hydrogen goes to the next carbon over there. Okay. These are the product for the second reaction. Okay. Let me go with the third reaction. Okay. Important reaction. Why it is important reaction means it is an exception, right? HBr with peroxide combination always gives anti-Marconico rule, right? Anti-Marconico rule, right? According to anti-Marconico rule, what is the statement actually? The negative part of the reagent goes to the carbon with more number of hydrogen. Okay. If you take this particular alkene here, what do we have here? We have CH2, right? Which has more number of hydrogen comparatively with carbon with one number of hydrogen, right? That's what bromine comes to the carbon with more number of hydrogen according to anti-Marconico rule. Okay. Let me write the product here. CH2 single bond, CH single bond, CH2. Okay. Now in the addition reaction double bond becomes what? Single bond, we know that. And where bromine will go according to anti-Marconico rule? Anti-Marconico rule, bromine goes to the carbon with more number of hydrogens, right? That's what bromine comes here, and hydrogen goes to the carbon with less number of hydrogen. Okay. That is what the products. Okay. Now during this addition reaction of hydrogen halide to the alkenes, right? One thing we have to follow that, what are the conditions and which rule we have to apply. Okay. Since all the alkenes are unsymmetrical alkenes, either we should go with Marconico rule or Anti-Margonical Rule. Okay, Marconico Rule means what? Only hydrogen halides without any peroxides over there. When it comes to Anti-Margonical Rule, only HBr and peroxide shows the Anti-Margonical Rule. Okay, that's what you have to remember. Next, okay, the last preparation of alkyl halides are going to be what? Halogen exchange reactions. Okay, what happens in the case of halogen exchange reaction means we will take alkyl halide. This X might be chlorine or bromine, with a metal halide. Okay, it might be fluorine or iodine. Okay, what happens is that exchanging of the reaction takes place. Okay, now we have seen the preparation of alkyl halides, right? Especially bromine and chlorine we have seen. Okay, but in this case, okay, what we will prepare is, in one case we will prepare alkyl iodide, in another case we can prepare what? Alkyl fluorides over there. Okay, let us take the Finkelstein reaction in which we can prepare alkyl iodide. Okay, let me take an alkyl halide. This halide might be chlorine or bromine. Okay, this halide might be what? Chlorine or bromine. Okay, what I am taking here is that I will take Ki or NaI, sodium iodide or potassium iodide. As I mentioned, it is an exchange reaction, right? What happens? This halogen exchanged with what? The iodine over there. What happens over there? Alkyl iodide formation takes place, followed by the formation of Kx. This X might be chlorine or bromine. Okay, in the case of Finkelstein reaction, what we can prepare over there? We can prepare iodides. Okay, you can take potassium iodide or sodium iodide also. Let us take this next reaction, Schwarz reaction. In this Schwarz reaction, we will prepare alkyl fluorides. Let me take Rx. This X might be chlorine or bromine again. Chlorine or bromine over there. What we will use it? We will use some fluorides of low reactive metals. Okay. Let us take AgF, silver fluoride, or we can take mercury fluoride, Hg2F2, or we can take SbF3, or we can also take cobalt fluoride. Any one of these, fluorides over there, right? Let me take, when this alkyl halides reacts with only AgF over there, means silver fluoride over there. What happens is that it forms alkyl fluoride followed by the formation of what? Silver halide. Silver halide. Okay. Here what is happening? This halogen is being replaced with what? Fluorine over there, right? Exchanging is taking place. That's what we are calling this one as what? Halogen exchange reactions. Okay. We have two named reactions. One is Finkelstein reaction and Schwarz reaction. In the case of Finkelstein reaction, formation of alkyl iodide takes place. In the case of Schwarz reaction, formation of alkyl fluoride takes place. Next, preparation of haloarenes. Okay, let us go with the first one by electrophilic substitution reaction. Okay, electrophilic substitution reaction, most of the times we will be remembering what? With a benzene ring. Okay, let us take up toluene. Okay, methyl benzene. This is CH3, methyl benzene. Okay, what do we have here? We should prepare an haloarenes, preparation of haloarenes, right? Now let us take a chlorine in presence of a Lewis acid in a dry ether conditions over there. Okay, in these conditions what happens is that formation of electrophile takes place. That electrophile is nothing but what? Chloronium ion. Okay, since CH3 group is what? Electron releasing group, it increases the electron density at ortho and para positions, right? As electron density increases, the charge of the electrons is negative, positive charge goes to the negative charges over there. That's what we'll get two products over there. One is orthochlorotoluene, this is CH3, chlorine will be substituted at ortho position, and we can also get a para product. We can also get what? A para product, CH3 and Cl. One is orthochlorotoluene, other one is what? Parachlorotoluene. Comparatively, right, parachlorotoluene is major one over there. Okay, the second named reaction over here for the preparation of haloarenes are going to be what? Sandman's reaction. This is one of the important reactions. For the Sandman's reaction, what we have to take first is we have to take aniline. We have to take what? Aniline. Okay, aniline or aminobenzene also will call aniline. This aniline on reaction with sodium nitride in NaNO2 plus HCl, sodium nitrite and HCl at 0 to 5 degrees Celsius. What happens is that this one turns into the salt called benzene diazonium chloride. Okay, N2 plus Cl minus. This is what? Benzene diazonium chloride. Okay, this is what? Benzene diazonium chloride. This benzene diazonium chloride on reaction with cuprous chloride, okay, gives halobenzene, that is chlorobenzene, that is Cl, chlorobenzene, followed by the releasing of N2 gas over there. Okay, this is what? Chlorobenzene now. Chlorobenzene. Here, from this step to this step, it's a kind of aromatic nucleophilic substitution reaction. Okay, nucleophilic substitution reaction. Okay, we can also prepare one more product by taking this one with Ki. Okay, K reacts immediately with benzene diazonium chloride immediately. Under warm condition itself, it will use aryl halide, that is iodobenzene. Okay, next, this is about the Sandman's reaction. Okay, first we have seen electrophilic substitution reaction, in which substitution takes place at ortho and para position because of the methyl group increases electron density at ortho and para position. Second one is Sandman's reaction, in which first step is formation of salt takes place, that is benzene diazonium chloride, and followed by the substitution, right? Aromatic substitution reaction gives what? Halobenzene over there. Halobenzene. These are all what? Preparations of alkyl halides and aryl halides over there. Okay. Now let us see the physical properties of these things which we have prepared now. Okay. Let us go with the melting and boiling points. Okay. Now if we take the red colored one, right, which is there as chloride, the blue colored one is what? Bromides. Yellow is what? Iodides. Chlorides, bromides and iodides. Chlorides, bromides and iodides. Okay. Now from top to bottom, if you go, right, what happens is that atomic number increases, atomic mass is also increases. Okay. Most of the cases, you just remember, boiling and melting points are directly proportional to their molecular weight. As we go from chlorine to bromides of methyl groups, right, what is happening? Atomic numbers and molecular mass is increasing. As molecular mass increases, what happens to the boiling points? Gradually increases. Okay. In the case of ethyl, chloride, bromide and iodide is also the same thing. Okay. Chlorides will have least boiling points, followed by bromides and iodides over there. In the case of propyl halides are also the same case. Okay. One thing we have to remember when it comes to boiling point, remember the molecular weight. Okay. Exceptional cases will apply those hydrogen bonding and all those cases. Normal conditions, you just remember the molecular weight. Okay. Boiling point follows what? Molecular weight. As molecular weight increases, what happens to the boiling points and melting points? Increases. Okay. Next, let us go with the question here. Arrange the set of compounds in the increasing order of the boiling points. Okay. We have a bromomethane. Let us take CH3, Br. This is one. Let us take bromoform, the second one, CHBr3. Let us take third one, chloromethane, that is CH3Cl. Let us take the fourth one. The fourth one is what? Fourth one is dibromomethane, that is CH2Br dibromomethane. Now, how do we have to say the increasing order of boiling point means? Now only we have discussed it is directly proportional to what? Their molecular weight, right? Now let us take all these compounds, right? Which one has the least molecular weight? The third one has the least molecular weight. Third one has what? Least molecular weight, because it is chloromethane, right? Chlorine is has less atomic mass comparatively with bromine. Let us go with monobromo product over there. That is the first one. Let us go with the dibromo. That is fourth one. Let us go with the last one, which has more molecular weight. That is what? Second one over there. Okay, that is bromoform. Okay. What is the order of increasing order of boiling points? Right. This is what the increasing order of the boiling point. As the molecular weight increases, the boiling point of the particular compounds also increases over there. Okay. Okay. Let us take the second one here. We have one chloropropane. This is one chloropropane. The first one. Second one is isopropyl chloride. This is isopropyl chloride. And the third one is, it is 1-chlorobutane. Third one is what? 1-chlorobutane. This is chlorine over there. Okay. This is the 1-chlorobutane. Now, out of all these three, right, which one has more molecular weight? This one has more molecular weight, right? Then what do we have to expect? The third one should be with more at boiling point comparatively with first and second one, right? If we take the first one and second one over here, what do we have? We have the same number of carbons, hydrogens and chlorines over there, right? That's what the molecular weight of these two is same. Then how do we have to identify over here? Okay. Now, if you take the first one, right, 1-chloropropane and isopropyl chloride over there, first one has more surface area, okay. Second one has less surface area because of the branch or substituent over there. As surface area increases, what happens? The attraction between the interparticle attractions is going to be increased over there. As attractions increases in this case, right, what happens? It requires more amount of energy to separate from one another, right? That's why the boiling point order is going to be the second one is the least one because of the branch, followed by the first one. Third one is the highest one. Why the third one is the highest one? Means it is a butane, not propane. Means more molecular weight, more boiling point. Okay, next. The chemical reactions of alkyl halides, right? We have three kinds of major reactions. One is nucleophilic substitution reaction, elimination reaction, and reaction with metals over there. Okay. Let us take one by one what are those and how can we discuss all these things. Okay. What is mean by nucleophilic substitution reactions? First, let us see what does it mean by nucleophile. Nucleophile we can just indicate with Nu minus over there. This minus itself indicates what? It is an electron rich species. Okay. Can readily known as what? Electron to the electron deficient species. Now, substitution means we know one species replaces another one or substitutes another one. The reaction, okay, one nucleophile replaces what? Another nucleophile. Let me write the definition, the generalized definition for the nucleophilic substitution reactions here. What is this one here? The reactions in which one nucleophile is replaced or substitution, okay, replaced or substituted is called the reaction in which one nucleophile is replaced or substituted by another, okay, nucleophile is called nucleophilic substitution reaction. Nucleophilic substitution reaction means incoming group is also should be electron rich, the outgoing group is also gets out as negative charge or nucleophile over there. Nucleophile over here, okay. Now let us take a simple reaction, okay. Let us take RX. This is a simple alkyl halide. Reaction with what? Nu means the nucleophile, right? What happens? As this one comes over here, the X gets out over there as minus. How the nucleophile is coming? The same way X also should go. Means Nu minus is coming, right? X also should go what? Minus over there. What happens? RNu plus X minus formation takes place, right? This is the incoming nucleophile. Getting a group is also what? Like leaving nucleophile will call, okay. Now, this nucleophile which is coming over there to attack the alkyl group from the alkyl halide over there, this is known as incoming group. Or incoming nucleophile also we can call. Now, the X is getting away from the alkyl halide, right? We will call this one as leaving group. Okay. Good incoming nucleophile increases the reactivity and the good leaving group also increases the reactivity over there. About this we will discuss later. This is about the generalized introduction for the nucleophilic substitution reaction. Okay. Let us see. Based on the different kinds of reagents, right, we will get different kinds of nucleophiles over there. I am not going to discuss all these things which are there in the board over here. As we have already discussed, we have Rx, Nu. What happens? RNu and X minus gets out, right? This is a simple generalized example for all nucleophilic substitution reactions over there. Okay. First, if we take NaOH over there, the nucleophile which comes out of NaOH or KOH is going to be what? OH minus. When this OH minus attacks the R over there from Rx, what happens? ROH formation takes place. This comes under the category called alcohol. Alcohols. If you take NaOR, out of NaOR, what is the what I can say? Sodium alkoxide. It gives what? Alkoxide ion, right? This alkoxide ion, when it reacts with R, ROR formation takes place. This comes under the category called ethers. Okay, like that. Based on the what I can say reagents, right? Different kinds of nucleophiles comes over there, and formation of products also takes place differently, and they'll give different kinds of what I can say, different category of products over there. Now what we can, I would like to mention is that I would like to mention about what I can say, AgCN and KCN, AgCN and KCN. Okay, when we take AgCN, RCN is formed, that is cyanide is forming over there, nitrile group. When we take AgCN over there, isocyanide is being formed over there, isocyanide being formed over there. Okay, why, like in the case of like potassium or sodium cyanide, like alkyl cyanide is being formed over there. In the case of silver cyanide, right, isocyanide is being formed over there, right. The reason for this one is Cation is being more ionic in nature, right. The donation of electron takes place from the carbon directly. That's what, when carbon donates, formation of new bond takes place between this carbon from the cyanide and the alkyl group over there. But when it comes to AgCN, right, it is more of covalent nature. In the case of covalent nature, electronegativity dominates over there. Donation of electron takes place through nitrogen, because of which we will get what? Isocyanide. Okay. With KCN we will get cyanide, CN bond, RCN bond. With silver cyanide, right, we will get NC bond, that is RNC. We will call it as isocyanide. Okay. And remaining all these things you just go through it. Next, let us go with the concept called optical activity. What does it mean by optical activity? Before we discuss about the optical activity, let me give you a small thing over here. Okay, let us take any light. Okay, any light. Okay, let us take the normal light from our home. Okay, let us take a light in our home. Now, if we take a particular light here, the normal light propagates in all the directions, right? Okay, it propagates in all the directions. Okay. In our home, when we switch on the light, what happens? The light propagates in all the direction. It won't direct in only one direction. It propagates in all the direction. Next, when this normal light passes through a prism over here, we'll call this one as Nicol prism. Okay, Nicol prism. It becomes a plane polarized light now. Plane polarized light means it can passes through only one direction. Okay, normally it is propagating in all the direction. When it passes through a prism over there, what is happening? It is like propagating through only one direction over there. When this one direction light or plane polarized light, right, pass it through an organic sample. Okay, let us take a sample tube here. Let us take a sample tube here. Let us take a sample tube. Okay, when this light passes through an organic sample, right, organic sample. Okay, let me take it down. Okay, there is a three conditions we can say. Okay, what is that condition? This is what the initial angle, right? Initial light over there. After passing through, the angle might be changed a bit towards right side. Okay, little. Okay, R. What is the second condition? This is the first condition. Let us go with the second one. Let us take the second one. This is the actual plane which is passing through the organic compound over there, organic sample. When it is passed through the sample, it may also deviate towards left with little angle over there. Little angle. Okay. This is the second one. Let us go with the third one. Okay, R. Like after passing this plane polarized light through this particular sample, right, we cannot see any kind of change in the angle over there. The angle remains same. Angle remains what? Same as the earlier initial one. Okay. Now, out of seeing all these things, right, where this deviation is happening in the case of angle of the plane polarized light, in the case of first one and second one, the deviation is being taking place, right? Deviation is being taking place. Means here, like a kind of rotation is taking place, right? Okay. Now, in the case of the compound which rotates the plane polarized light towards right side or left side are called optically active compounds. Optically active compounds. Optically active compounds. Okay. Now, if you take these two cases, right, in the first one and the second one over there, now which side it is deviated? Actually, it is deviated towards right side, right? Okay. The samples are the compounds, organic compound, which rotates the plane polarized light towards right side, right? Towards right side. Those compounds are known as dextrorotatory compound. Dextrorotatory compound. Okay. This compound will be simply indicated with small d, or we can also indicate it with what? Plus sign, a positive sign. Okay, you would have seen what I can say, D plus glucose, okay, dextroglucose, levofructose, like that and all you would have seen, right? That is based on what? optical activity it is. Okay. Now if you take the second rotation, right, it is deviated towards left side, means anti-clockwise it is deviated, right. The compound which rotates the plane polarized light towards left side are known as levorotatory compound. Levorotatory compounds. Levorotatory compounds. These levorotatory compounds will simply indicate it with small l or minus. Now what is the last one? We have the third one. In the case of third one, what do we have? There is no change in the angle of the plane polarized light over there, right? The compound which doesn't change in the angle of the plane polarized light are called optically active compounds. Optically inactive compounds, sorry. Optically inactive compounds. Inactive compounds. They cannot show any kind of deviation in the case of what? This plane of the plane polarized light. Okay. Generally, I am not specifically mentioning here. Generally, what happens is that the chiral carbon containing substances, shows optical activity. Okay. The chiral compound containing substances shows what? Optical activity. What is mean by chiral carbon means, if you take any carbon, okay, any carbon, if any carbon is connected with 4 different groups, right, let us take like A, B, D, E, around this carbon, right, whatever the groups are connected over there, all are different, not identical one, right. These kind of compounds are called chiral carbon, right. Generally, chiral carbon containing substances shows what? Optically active. Okay, if it is like there is no chiral carbon in the sense what? We cannot expect optical activity. It is a general one, okay, not specifically mentioned, remember. Okay, let us go with the next one. Next, as we have already mentioned, right, the general light propagates in all the direction. When it is passed through a particular prism over there, the plane remains same over there, propagates in only one direction over there. After what I can say, this plane passing through a sample tube, right, which contains the organic compound, right, it may deviate or may not be deviating over there, right. Okay, we can see from here over there. Okay. Now, if it is deviating from the actual angle over there, we'll call this compound as optically active compound. If it is not deviating over there, call it as optical inactive compounds. Okay, which compound shows the optical activity? As we have already mentioned, chiral carbon containing substances shows what? Optical activity. Okay, next. Okay, let us go with the SN2 reaction. Okay, now it is also nucleophilic substitution reaction only, but we have to remember it is a biomolecular reaction. Okay, let us give few important points related to biomolecular substitution reaction. Okay, let us take the first point here. If you take primary, secondary, tertiary alkyl halides, right, primary alkyl halides readily undergo like SN2 reaction followed by secondary and followed by tertiary. Okay, this is what? Reactivity of alkyl halide. Which alkyl halide readily undergoes SN2 reaction? Primary greater than, secondary greater than, tertiary. Okay. Now, second one. What solvent is used in the SN2 reaction? Means polar aprotic solvent is used. Polar aprotic solvents. Polar aprotic solvents is used. What do you mean by polar aprotic solvent? Polar solvents in the sense what? The one which has more dielectric constant. Aprotic means what? They cannot form hydrogen bonding. Okay. Polar aprotic solvents are preferable for SN2 reaction. Okay. The molecularity of the reaction. It is already mentioned by means what? 2. Molecularity of the reaction is what? 2. How many molecules are taking place in the main step over there? 2 molecules are being participated over there. Okay. The next one, order of the reaction. Order of the reaction is also 2. Rate is directly proportional to concentration of the substrate, that is Rx, and concentration of the nucleophile also. 1 plus 1, 2, right? That's what the order of the reaction is also 2. Now let us take how the reaction takes place. Okay, no intermediate is present. Okay, no intermediate. Okay, only transition state. Transition state, or we can also call it as activated complex. Activated complex over there. Activated complex over there. Okay, let us take a simple reaction over here. Okay, let us take a simple reaction. Okay, let us take H. Let me take primary, what I can say, CH3 CH2 X, primary alkyl halide. Okay, primary alkyl halide. What happens here when we take a particular reagent? Okay, nucleophile comes and attacks from the back, and formation of activated complex takes place, right? Transition state formation takes place over here. Transition state means what? Let me take it here. X, nucleophile is attacking from the back side. X is getting out as X minus. Remaining what do we have? We have CH3 and we have hydrogen and we have hydrogen. Okay. Now this is what the activated complex, CH3 H nucleophile and X over there. It seems to be something like trigonal bipyramidal, right? The geometry. Remember, the geometry of the transition state in the SN2 reaction is what? Trigonal bipyramidal. Now the charge which is dominating in the transition state or activated complex is what? Negative charge, right? That's what, if electron withdrawing group containing substrate is there, that is going to be more reactive towards SN2 reactions. Okay. In the final step, what happens? Nucleophile comes here, carbon, CH3, H and H over here, and followed by the leaving group over here. Okay. Now we have to remember one thing. Okay. Now if it is a chiral carbon, right, where the nucleophile is attacking over there from the back side. From the back side means, you just remember one point here. One point. What is this one? Chiral carbon, chiral primary substrate, especially primary substrate. In this reaction gives inversion product. Inversion product. Why it is inversion product means what we have to say? The configuration of the reactant and the product is going to be different, because the nucleophile comes exactly back to the leaving nucleophile over there, because of which we will get what? Inversion product. Okay. What are the things we have to remember here? In this case, right, what happens is that primary alkyl halides greater than secondary alkyl halides are greater than tertiary alkyl halide in terms of reactivity of alkyl halides towards SN2 reaction. Polar aprotic solvent is used. The molecularity of the reaction is 2. Order of the reaction is 2. Rate of the reaction depends on what? Concentration of the substrate and the incoming nucleophile, or concentration of the substrate and what I can say, incoming base over there. Okay. No intermediate is present, only transition state is present. The geometry of the transition state is going to be what? Trigonal bipyramidal. The charge in the transition state is going to be negative. If the primary substrate contains any electron withdrawing group, right, that is going to be more reactive towards SN2 reaction. Okay. Now chiral carbon containing primary substrates gives what? Inversion product. Means the configuration of the reactant and products are going to be what? Different, opposite to one another. Okay. Let us take a potential energy diagram of SN2 reaction. Okay. It is a single step reaction. There is no multi-step reaction. It is very, very single step. You have to remember, single step reaction. Okay. Single step reaction means we will take the reactant, just goes and formation of product takes place, right? Now let me take, I am not mentioning whether it is exothermic or endothermic. I am just ideally taking a particular reaction here. Okay. This is the energy versus reaction coordinates. Okay. Now initially what do we have? Primary alkyl halide. And what do we have? We have the nucleophile also. Here what is happening? Transition state or activated complex is being formed over there. In the final step, what is formed over there? We have the product, that is RNU is being formed over there. Okay, this is a single step reaction, right? That's what we have to take. Only one transition state in the reaction. This is all about SN2 reaction. This is all about what? SN2 reaction. Okay, let us go with SN1 reaction. Let us go with SN1 reaction. What does it mean by SN1 reaction? Let me write it here. Let me take some of the points related to SN1 reaction. What is this one? In the case of SN1 reaction, right, let us go to the reactivity of alkyl halides, right. Tertiary alkyl halides are more reactive, followed by secondary alkyl halides, followed by primary halides in terms of reactivity. Reactivity of Rx, which alkyl halides readily undergoes SN1 reaction means what do you have to say? That is, tertiary alkyl halides readily undergoes SN1 reaction followed by secondary and primary. Now, what is the reagent is used in the, what is the solvent is used in the case of SN1 reaction? Here is that polar protic solvent is used. Polar protic solvent is used. Okay, let us take the third point. It is not a single step reaction, right? That's what we will call it as non-concerted reaction. Non-concerted reaction. In this non-concerted reaction means intermediate is present, right? What is the intermediate? Intermediate is carbocation. Okay, we'll just write it as carbocation. We know the order of carbocation stability, right? Tertiary carbocations are more stable than secondary carbocations are more stable than primary. That's what the order of reactivity of alkyl halides are also what? Tertiary is greater than, secondary is greater than primary over here. Okay. Now let us take the another point here. Another point over there. Okay. Chiral carbon in this reaction gives racemic mixture. Racemic mixture will just indicate with plus and minus. Racemic mixture is generally optically inactive. We have already mentioned what is meant by optically active and what is meant by optically inactive, right? Racemic mixture, though it contains chiral carbon, it is optically inactive because of external compensation. Okay. External compensation. Okay. Now let us take one more point here. Let us go to the molecularity. Molecularity means molecularity of the reaction is 1. That's what we will call it as unimolecular nucleophilic substitution reaction. Why molecularity is 1 means it's a multi-step reaction, right? In the rate determining step, only one substrate is there. Next, what about the rate? Rate is directly proportional to only tertiary alkyl halide. Okay, not on the nucleophile. Okay, 0. Okay, anything to the power 0 is what? 1. That's what rate depends on only what? Tertiary alkyl halides over there. That is why the order of the reaction is going to be what? 1. Order is going to be what? 1. These are all what the generalized data about what? A nucleophilic substitution reaction in terms of unimolecularity. Okay. If you take SN1 reaction, this is what the important data which we have to remember. Okay. If you wanna go through it, just pause the video for 1 or 2 minutes. Just go through it and go for the mechanism of it. Okay. I'm just going to the next slide. Okay. Let us see how the SN1 reaction takes place. Here. Okay. Now let us take a tertiary alkyl halides. For example, let us take R dash, R double dash, and X. Okay. The first step, what happens is that in the case of first step, elimination of leaving group takes place, right? What happens? R C plus R dash and R double dash plus X minus over there. Okay. Now we know this is the carbocation. The hybridization of this carbocation is what? sp2. sp2 means what is the geometry? Trigonal planar, right? Means these 3 bonds are on the same plane over there. Okay. Let us take the second step. What happens? Let us take the carbocation here. Okay, double dash over there. Okay. Now what do we have? We have an incoming nucleophile, right? This incoming nucleophile, since it is planar, right? This incoming nucleophile can approach from the above the plane. This can also approach from the below the plane over there. It can come from the below the plane or above the plane also. We'll get 2 kinds of products over there. Okay, let me take the first product here. What is the first product? R dash, Nu, and R double dash. And what is the another product over there? Nu, C, R dash, R double dash, and RK. Now in this case, right, we have two products here. In the case of first one, right, where the incoming nucleophile is there, the same side of X over there. The same side of X means what we will call it as retention product. Retention product. Retention product, okay. Now in the case of second one, where do we have the nucleophile? It is opposite to that of initial leaving group, right, over there. That's what we will call this one as inversion product. Inversion product over there, okay. Now in this case, right, if we get like, there are two possibilities because it is planar. Nucleophile can come from the above the plane or below the plane. If we take this one is 50%, this one is 50%, okay. Let us take the chirality of the carbon here. What is the chirality of the carbon? If we take this carbon here, all these groups which are there around the carbon are 4 are different group, right? That's what this is chiral one. This is chiral. Okay, this is also chiral because four groups are different groups over there. Though these two have what I can say chiral carbon, right? As a mixture together, it is optically inactive. Optically inactive. We'll call this one as racemic mixture. We'll call it together, it is known as what? Racemic mixture. Racemic mixture. Racemic mixture. One thing we have to remember right here, what is that? This is the racemic mixture together, right? Retention product and inversion product together is what? Racemic mixture we know. This is optically inactive. Why it is optically inactive means, for example, let us take the first product which is formed over there. Let us take it is a positive, like what I can say, dextrorotatory compound. We are just assuming this one is what? Dextrorotatory compound. Okay. Second one we are assuming it as levorotatory compound. Dextrorotatory, levorotatory. Let us take the first one, rotates the plane polarized light towards right side around 30 degrees, right? Let us assume the second one, what I can say, it's like it rotates the plane polarized light towards the left side around 30 degrees, right? Plus 30 degrees and minus 30 degrees becomes what? 0 again, right? The rotation of the first compound will be compensated with what? The second compound. That's what we are calling this one as what? Due to external compensation, the racemic mixture becomes optical inactive. The rotation of the first compound will be compensated with what? The rotation of the second compound. That is why the racemic mixture is optically inactive. The racemic mixture is what? Optically inactive. Okay, this is the first step which we are calling it as slowest step or RDS step. In the RDS step, we have only one substrate, right? That's what rate depends only on the one substrate. That's what the order of the reaction is also going to be what? 1, and the molecularity is also what? 1. Next, which of the which among the following properties makes tertiary alkyl halides particularly inert to SN2 reaction? In the SN2 reaction, what we have mentioned, the primary alkyl halides are greater than, secondary alkyl halides are greater than tertiary alkyl halides in terms of reactivity, right? In terms of reactivity. Now, like it is not about insolubility, there is no particular mention about insolubility, there is no instability, there is no inductive effect. All these things we did not discuss. In terms of stability, right, when carbocation is formed over there, then we can go with the stability and all those things. But there is no mention about these things, right? Whatever the remaining things we have, that is a steric hindrance, okay? How the steric hindrance affects the SN2 reaction over there? Let us take this particular diagram here. This particular diagram, okay? We have a methyl group, primary, secondary, and tertiary carbocations, like alkyl halides over there, right? Now, the leaving group and incoming group approaching takes place in the same time over there, since it is a single step reaction, okay? Now, in the case of first one, right, it can easily approach from the back side. In the case of second one, because of the bulkier group, becomes a little difficult. As we go to the second one, what happens? We have two bulky groups, right? Approaching to the carbon becomes very difficult. And in the case of third one, nucleophile becomes, it becomes very difficult for the nucleophile to approach the carbon because of the steric hindrance, because of the size of the adjacent groups over there, right? That's what the answer is what? Steric region. Steric hindrance, okay? Let us go to the next one. Which are the following pairs halogen compounds which would undergo SN2 reaction? SN2 reaction means what? Primary is greater than, secondary is greater than tertiary in terms of reactivity, as we have already discussed, right? What is this one here? It is primary because this carbon is connected to only primary carbon. This is what? This is the carbon where it is connected to two carbons over there, right? This is secondary. Now let us here also we identify this is primary, this is also primary. Out of these two, primary and secondary are there, right? Which one readily undergoes SN2 reactions? As we have already discussed, primary will readily undergo SN2 reaction. That's what this compound will readily undergo SN2 reaction. If you take these two are primary only, but the halogens are different. Iodines are and chlorines. Iodines and chlorine means what we have to remember? The leaving group nature, leaving group order. Because of the bond length, right? Ci bond is weaker comparatively with Cl over there. That's why the first one will readily undergo what? SN2 reaction. SN2 reaction. Okay. And the next type of reaction is what? Elimination reaction. Elimination reaction. Okay. We have three kinds of elimination in general. We have alpha elimination, we have beta elimination, and we have gamma elimination. It is based on the position where the groups are being eliminated. Okay. From 1 position elimination takes place, that is alpha elimination. From 1 2 position elimination takes place, we will call beta. 1 2 we will call beta. From 1 3 if takes place, we will call this one as gamma over there. Okay. Let us take these two here. This is the one, like it is not directly involved, but indirectly it is involved in the organic mechanisms over there. Okay. If you take for example chloroform, in presence of base, elimination of halogen, like hydrogen takes place, we will get what? CCl3 minus. In the following step, what happens is that elimination of chlorine takes place and formation of dichlorocarbon takes place. Dichlorocarbon. Now, in the case of first one, hydrogen went outside, and here chlorine got out, right? These two groups are being eliminated from the same carbon, right? That's what we are calling this one as 1-1 elimination. 1-1 elimination over there. Okay. For example, let us take the second one here. Let us take 1-2 carbons here, hydrogen and halogen. Okay. In presence of a particular base, what happens is that elimination of these two groups takes place and formation of double bond takes place between adjacent carbons over there, right? Elimination of groups are taking place from 1 2 positions, right? That's what we are calling this one as gamma. If it is from 1 3, we will call this one as beta. 1 3 we will call this one as gamma over there. Okay. Just remember these examples right here. Okay. Let us take an example right here. Okay. Let us take an unsymmetrical alkene, that all like hydrogen halides, alkyl halides, that is H3 CH okay 2 CH X and CH3. We will take this one as CH H. We will take this one as CH2H, because number of hydrogens are going to be same only. We will take H here. Okay. We will take two possibilities. Okay. In presence of a bulkier base, we will take alcoholic KOH and alcoholic KOH. Okay. In these two cases, what happens? Let us see simply. Now we have halogen here. We have a halogen. This is the first carbon. Let us take. But I'm not like giving the IUPAC numbering order here. I'm just taking this carbon as first carbon. Okay. This is second carbon. This is also second carbon, right? Now what are the possibilities we have? This is a dehydrohalogenating reagent. Hydrogen and halogen gets out over here. In the case of this one, right, at the first carbon we have halogen. Along with this, on the adjacent carbon we have two possibilities. One is terminal hydrogen is there, and we have internal hydrogen is also there. Okay. Now let us take with the terminal hydrogen. When terminal hydrogen gets out, what happens? Formation of double bond takes place between 1 and 2. That is CH3, CH2, CH, double bond, CH2. This is the terminal double bond. Okay. Now what we will do is, we will take this hydrogen and this halogen. When these two gets out, what happens? Double bond formation takes place between these two internal carbons over there. Okay. That is CH3, CH, double bond CH, single bond CH3. Okay. Now what we have to remember here is that since the double bond is located in between these two carbons, right, between the terminal carbons over there, we will call this one as terminal alkenes. Okay, this is what we call it as internal alkenes. Okay, out of these two, which is going to be the major for the reaction? Okay, we cannot say directly, but from a rule called Sagejeff rule. What's the rule? Sagejeff rule. Okay, or Zaitsev rule. Jetsov's rule. Okay, based on these two rules, right, the major product we can going to like identify over there. Okay, according to these rules, right, which alkenes are going to be measured in the sense the internal alkenes are more stable. According to Seder's rule or Jetsov's rule, which alkenes are going to be more stable? Internal alkenes are more stable. That's why the internal alkene product, right, this is going to be what? The major one. The major one. Understood? Okay, according to this Seder's rule, we should always remember the internal alkenes. If internal alkenes are formed, they are going to be major one. Okay, sometimes terminal alkenes are also more stable. In a different case, we need not to worry about this one. Okay, now let us go with the next one. 2-bromobutane on dehydration gives 2-butane, which is also called which product over there? Okay, let us take 2-bromobutane. Okay, on this elimination reaction gives 2-butane, right? Means like between two carbons, right? It seems to be something like internal alkene. Internal alkenes. Okay, it is in between the internal alkenes, internal carbons, okay, not in the terminal one. Okay, according to which rule it is? Actually, Seder's rule, right? We will call this one as Seder's product. Seder's product. Okay, next 1-chlorobutane on reaction of alcoholic KOH. Okay, let us take CH3, CH2, CH2, CH2 and Cl. Okay, on the first carbon it is there. Okay, on reaction with alcoholic KOH. You just remember this is an example for the dehydrohalogenating reagent. Dehydrohalogenating reagent. Alcoholic KOH or NaOH will take it as dehydrohalogenating reagent. Okay, halogen and hydrogen gets out over there. Now we just see the possibilities, right? What are the possibilities? How we have only one possibility. Okay, 1,2 elimination takes place. The second carbon only we have this hydrogen, right? Right side we don't have any kind of possibilities over there. That's what we'll get only one product where the double bond formation takes place between 1-2 carbons here. Okay, let me take the product here. That is CH3, CH2, CH, double bond CH2. Only one possibility is there, right? There is no other possibility over there. That's what we'll get over there. 1 butane or 2 butane over there. We'll get 1 butane because numbering starts from the double bond carbon, terminal double bond carbon over there. That's what the answer is, 1 butane. Okay, next. Let us go with the two conditions here, elimination versus substitution. Okay, in which conditions elimination takes place, in which condition substitution takes place. Okay, for example, if you take CH3, CH2, CHCl and CH3. So let us take two conditions here. What are those conditions here? First we will take aqueous KOH. Okay, in the case of second one we will take alcoholic KOH. Okay, in these two cases what is happening here is that in the case of aqueous KOH, right, this is the smallest base. It favors substitution reaction, SN type reaction, and formation of alcohols takes place. Chlorine gets substituted, CH3, CH2, CH, OH and CH3. This is a substitution reaction. But when it comes to alcoholic KOH, right, this is a bulkier base. What happens is that it favors elimination reaction. Beta elimination takes place. Beta elimination means from 1-2 position according to the Seder's rule, elimination takes place, double bond formation takes place in between these two carbons over here. Okay, that is CH3, CH, double bond, CH, single bond, CH3. If you take these two particular reactions here, the substrate is same, but the reagents are different, right? One is aqueous KOH, second one is what? Alcoholic KOH, right? Aqueous KOH is a smaller base, favors SN type reaction, and the alcoholic KOH is what? A bulkier base, favors what? Elimination reaction. Okay, first condition is the smaller base favors substitution over elimination reaction. The small base what? Favors what? Substitution reaction over elimination reaction. Based on the size of the substrate also, there is a competition in between elimination and substitution. What is this one? Let us take here. Okay, now what do we have? We have what I can say, we have a base. What is this base? It is a bulky base. Bulky base. Now what do we have here? We have a small base. Small base over here. Okay. Now since we have a bulkier base, right? Instead of approaching to the what I can say, carbon, right? For the substitution reaction, what is happening here is that it is just abstracting the hydrogen from the adjacent carbon, by which these electrons which are there between carbon and hydrogen bond, right? These two electrons are utilized for the formation of double bond between carbon and carbon, by which elimination of leaving group takes place. By the bulkier group. If you take the small group, right, there is a space to enter to the carbon where the halogen is being attached over there, and it makes bromine to gets out over there, and it favors what? Substitution reaction. Okay. One is what we have discussed over there. The small base favors substitution reaction over elimination, but the bulky base favors elimination over substitution reactions over there. Okay. And another condition is also there. What is that condition actually? High temperature favors elimination reaction over substitution. High temperature also matters over there. Okay. When you take the elimination reaction, right? If you take alkyl halides, right? The reactivity of alkyl halides towards elimination reaction is going to be what? Tertiary alkyl halides are greater, followed by secondary, followed by primary. Primary. Okay. Next. Now let us see the another reaction called reaction with metals, right? For example, if we take any simple alkyl halides with magnesium in presence of dry ether, what happens is that it forms a particular reagent called Grignard reagent, RMGX. Okay. What does it mean by RMGX here is that we will call this one as Grignard reagent. Okay, name after the scientist who prepared Grignard reagent at the very first time. Okay. Now what happens? Alkyl halides on reaction with magnesium gives what? Alkyl magnesium halide. That is what we call it as Grignard reagent. Okay. This is one of the reaction with metal. And the another reaction is called Wurtz reaction. One of the important named reaction. Wurtz reaction. This is used for the preparation of alkanes. Okay, formation of new CC bond formation takes place. Here. Okay. What is this one? Let us take 1 mole of alkyl halide with sodium metal. Okay, 2 moles of sodium metal and another mole of alkyl halide. What happens? This halogen gets out along with the sodium, and formation of what takes place? Let us see. It takes place in presence of dry ether. It takes place in presence of what? Dry ether. Okay. Between these two alkyl groups, there is a new bond formation takes place. Between these two alkyl groups, formation of new bond takes place. That is R plus what do we have here? NaX, right? 2 NaX formation takes place. Okay. I mentioned that is a new bond formation takes place between two carbons, right? Let us take an example. Let us take CH3X plus 2Na plus XCH3 in presence of dry ether condition only. What happens here is that halogen gets along with the sodium and formation of new bond takes place between carbon and carbon. This is the methyl group. H3C, and the new methyl group coming over there. Plus 2NaX. If you take this particular alkane over here, what is happening here is that there is a new bond formed between two carbons over there. Right? Wurtz reaction can be used for the preparation of alkanes, right? By taking methyl halides, what we have prepared? Ethane. If you take ethyl halide, we will take butane. If you take propyl halide, we will take hexane. Okay. Based on the number of carbons which we will take, we will prepare the higher number of alkanes over there. Next. Now let us take the reaction of haloarenes, right? We have discussed the substitution reaction in the case of haloalkanes, but let us go with the haloarenes also, right? Now let us see nucleophilic substitution reaction in terms of haloarenes, right? They are less reactive towards nucleophilic substitution reaction due to the following reasons. What are those following reasons over there? First, the resonance effect. The second one is difference in hybridization of the carbon atom in CX bond in the haloarenes. The third case, instability of the phenyl cation. The fourth one is what? Possible repulsions, right? Okay. All these things step by step let us discuss why these haloarenes are less reactive towards nucleophilic substitution reaction. Let us take the resonance effect over there. Resonance effect, okay. If you take a haloarenes first, what happens in the case of haloarenes are, we have the lone pairs and the pi bond in the benzene ring which are in a conjugation, right? That's what delocalization takes place. When delocalization takes place, what happens is that there is a double bond formation takes place between halogen and the carbon. Then what happens? Delocalization takes place. Okay, anion and pi bond delocalization takes place. The new bond formation takes place between these two carbons over there, and the double bond remains on the between carbon and halogen over there. And then the next step, what happens? This anion and the pi bond delocalization takes place. The negative charge formation takes place at the ortho position. There is a new bond formation takes place here, and the double bond remains same over there. Again, these two are in conjugation. Delocalization takes place. When delocalization takes place, what happens? The double bond between carbon and halogen becomes a single bond. Means it is not permanent. It doesn't mean that it is always be in a single bond character. Okay, we have a kind of partial double bond character. Partial double bond in between carbon and halogen, right? We know that's one thing, right? Bond length is inversely proportional to bond strength and inversely proportional to what? Bond order also. If you take the simple CX bond, the double bonded CX, okay, over here, what happens here is that the bond order is 1 here, the bond order is 2 between carbon and halogen over there, right? As the bond order increases, what happens to the bond length? As bond order increases, bond strength also increases, but bond length decreases. As the bond strength increases, it becomes very difficult to leave the halogen group over there. That is why, because of this partial double bond character, due to resonance, it restricts itself to undergo what? Nucleophilic substitution reactions. Okay. Now let us take the second region. Okay. Difference in hybridization of carbon atom in CX bond. For example, if you take haloarenes, what happens is that we have carbon which is sp2 hybridized carbon. Okay. Now if you take a simple alkyl halide, right? This is sp3 hybridized carbon. Okay. In this case, right, the percentage of S is going to be what? 33.3% of S. In this case, the percentage of S is going to be what? Once again, here it is 25%. Here it is 33.3% in this case of S character. Now, from sp3 to sp2, right, the percentage of S is increasing from 25 to 33. As the S character increases, electronegativity increases of the carbon. As the electronegativity increases, what happens is that the shared pair comes to the closer to the carbon over there, because of which bond length of CX bond decreases. Now we have already discussed earlier, bond length is inversely proportional to what? Bond strength. As bond length decreases, bond strength increases. As bond strength increases, the amount of energy which is required to break the bond increases, because of which it requires more amount of energy to break it, right? That's what, it's also one of the reason why the haloarenes readily not undergo what? Nucleophilic substitution reaction. This is the second reason. Let us go with the third reason. Replacement by hydroxyl group. Okay, for example, if you take a simple chlorine here, let us take a simple chlorine. Before that, let me take another reason. Okay, we have discussed two things. Okay, let's go with the instability of phenyl cation. Okay, in the case of SN1 reaction, if it is aromatic SN1 reaction, what is the intermediate? Carbocation should take place, right? Formation takes place, right? In the case of benzene, right, like carbocation takes place on this carbon where the halogen gets out over there, right? This carbocation is highly unstable because of the adjacent carbons over there. Adjacent carbon, right? The hybridization of adjacent carbon is what? sp2. From sp3 to sp2, S character increases, electronegativity increases. Because of the electronegativity, the magnitude of charge increases. the stability of the phenyl cationase decreases, right? That is one of the reasons. And let us possible repulsions also takes place. What is the possible repulsions means? For example, if you take what I can say benzene, right? Benzene itself is a nucleophile. Benzene itself is what? Nucleophile. If incoming nucleophile comes, between nucleophile and nucleophile, what happens? Repulsions takes place, right? Because of this particular reasons, right? Because of these 4 reasons, haloarenes are what? Least reactive towards nucleophilic substitution reaction. Nucleophilic substitution reaction. Let us take an example. Replacement by hydroxyl group. Let us take alkyl, like what I can say, aryl halide over there. Let us take an X over there, or possibly let us take a CCl, chlorobenzene, right? Let us take an NaOH group, at 623 Kelvin and 300 atmospheric pressure. Okay, we are not making the chlorobenzene to react with what I can say sodium hydroxide to form phenol under normal conditions. But what are the conditions we are applying over there? We are applying 623 Kelvin and 300 atmospheric pressure. 300 atmospheric pressure means we can simply say it as it is an extreme condition, not under normal condition it is happening, right? Now if we take the another example, let us take the chlorine with one electron withdrawing group. Okay, the reaction takes place with sodium hydroxide at approximately 423 Kelvin. Okay, and what happens? Formation of phenol takes place. Okay, what phenol? Orthonitrophenol, right? Orthonitrophenol. Let us take 2 more what I can say electron withdrawing group containing chlorobenzenes, right? NO2 here and NO2 also here. Okay, what are the conditions are required? Let us take NaOH, and the less than that of the temperature which we have taken gives what? A phenol over there. NO2 and NO2. If you take the last one, right? This is the first one, second one, and the third one. Third one will take trinitrophenol, right? Let us take trinitrochlorine. This is chlorine. NO2. Now if you take this one, right, we will just react this one with H2O, just a simple warm condition. Okay, what happens is that this chlorine is being replaced with what? OH group over there. What happens here is that formation of OH group takes place, okay, by the nucleophilic substitution reaction, especially aromatic nucleophilic substitution reactions. Okay, now we have to remember one particular condition here. From chlorobenzene to nitrochlorobenzene to dinitrochlorobenzene, then trinitrochlorobenzene, right? If you see the conditions which we are applying are gradually decreasing, right? Means simply we can say by introduction of electron withdrawing group, that is NO2 group, the ease of formation of phenol becoming very easy over there, right? That is why we just say because of the introduction of electron withdrawing group to the chlorobenzene, right, they will readily undergo what? Aromatic nucleophilic substitution reactions, right? Now the question is why it is happening. The question is why the electron withdrawing group containing chlorobenzene, right, readily undergoing nucleophilic substitution reaction, right? Now we know that incoming group is nucleophile, which is negatively charged. We know benzene itself is what? Nucleophile, right? Means what? This is also negatively charged over there. During these things, what is happening here is that now if we introduce electron withdrawing group, they will withdraw the electrons towards themselves, right? They will withdraw the electrons towards themselves. NO2 goes to, electrons goes towards what? NO2 groups. As we introduce more number of electron withdrawing group towards on the benzene, what happens is that electrons moves away from the benzene and electron density on the benzene decreases. As electron density on the benzene decreases, electron deficiency increases. As electron deficiency increases, nucleophile can readily attack the benzene ring over there and substitute the chlorine to form the phenol over there, right? That is why as we introduce the NO2 groups, right, more electron withdrawing groups, they will readily undergo what? Aromatic nucleophilic substitution reaction, right? Out of all these 4, 1, 2, 3, 4, this is the fourth one, right? What is the order of reactivity towards nucleophilic substitution reaction in the sense? The fourth one is greater, then third one, then second one, then first one. We have already discussed why it is so, right? Let us go with the next one. Let us go with the electrophilic substitution reactions, right? we have four kinds of reaction. One is halogenation, nitration, sulfonation, and Friedel-Crafts reaction. Okay, let us see one by one what are those. Before that, let us see like how the what I can say like resonance or delocalization takes place with the halogen here. With the halogen, what is happening here is that we have an halogen with a lone pair, right? What happens? Delocalization takes place over there. Delocalization takes place. There is a negative charge formation takes place on the benzene ring, right? This is a negative charge over there. A double bond formation takes place between carbon and halogen. The remaining bonds remain same over there. Between like anion and pi bond again are in conjugation over there, right? Conjugation. Then again, what happens here? There is a delocalization takes place between anion and pi bond. There is a new anion formation takes place at para position, and double bond between carbon and halogen over there. Again, these two are in conjugation, right? These two are in conjugation. Okay, these two are in conjugation. Again, delocalization takes place. What happens here? New anion formation takes place at ortho position, and double bonds will be there. Okay, and again delocalization takes place, and we will get the first structure. Okay, during this delocalization, right, what is happening here is that anion is there at ortho position, anion is there at the para position, anion is there at the ortho position again, okay. Now I would like to mention one particular thing here. What is that? The negative charge electron density is increasing at ortho and para positions because of the halogen group over there. Because of what? Halogen group over there. What kind of reaction is this? Electrophilic reaction. Electrophilic means what? They love the electron. They love the negative charge. Now the electrophile goes to the negative charge, right? Where the negative charge is there at ortho and para position. That's what electrophilic substitution reaction with the halobenzene takes place at ortho and para position. Why with electron, like what I can say, halogen electrophilic substitution reaction takes place at ortho and para positions means what you have to say? It is because electron density with the halogen increases at ortho and para position. Let us go with the halogenation, nitration, sulfonation, right? Let us take the halogenation first. First one is halogenation. Okay, I am not going to write the mechanism of the electrophilic substitution reaction. It is a common reaction. What is this? First, formation of electrophile takes place, formation of sigma complex takes place, and elimination of proton takes place, right? These are all three steps are there, but I am just going to write the direct reactions. Okay, let us take X. It might be any halogen, okay, especially chlorine and bromine here. What we will do is, we will just react with what I can say halogenation, right? Let us react with Cl2 in presence of AlCl3, and under dry ether condition. What happens here? Since it is Lewis acid, it can accept the pair of electron from the chlorine, and it generates what? Cl plus and AlCl4 minus. Okay. Now what is this one? This is the electrophile, right, which is seeking for the electrons, where the electron density increases with the halogen, as we have already discussed, at ortho and para position, right? We will get two products here. What are those two products here? One is orthochloro product, plus we will get another product that is para-chloro product. Here the para one is major one. Para one is what? The major one. Okay. Let us take the second one. Okay. Nitration. Most of the time, the nitrating mixture means we will be taking HNO3 and H2SO4. Sometimes, based on the condition, we can generally take HNO3 alone. Okay. Let us take the halobenzene here. Halobenzene on reaction with HNO3 plus H2SO4. Okay, we will call this one as nitrating mixture. What happens is that these two generates NO2 plus nitronium as a electrophile. Since it is electrophile, it will goes to the carbon like ortho and para positions over there, right? We'll get ortho and para products. X NO2 at ortho position and NO2 at para position. This is what? Para. Para one is what? Major one. Major one. Okay. Now let us go with the third reaction, that is sulfonation reaction. What is this one? Sulfonation reaction. The third one is what? Sulfonation reaction. We will just take 2 moles of sulfuric acid. for sulfonating as a sulfonating reagent. Okay, we will take halobenzene and we will take sulfonating reagent, that is 2 moles of H2SO4. 2 moles of H2SO4. It generates what? HSO3 plus. HSO3 plus. Okay. Then what happens? Ortho and para substitution takes place, because at ortho and para position, halogen increases the electron density, right? SO3H, benzene sulfonic acid, plus at para position, substitution takes place. X SO3H. This is again the major one. This is again the major one. Okay. Let us take the fourth one, Friedel-Crafts reaction. Friedel-Crafts reaction. Friedel-Crafts reaction. Okay. We have two Friedel-Crafts reaction. One is alkylation. And the second one is acylation. Okay, let us take both the reaction. Let us take the first one, alkylation. Let us take chlorobenzene here. In presence of RX and the Lewis acid, let us take ALX3. If you take ALCL, like RCl, it will be ALCl3 over there. What happens? It generates what? R plus alkyl cation. Okay, carbocation generation takes place. Goes to the ortho and para position again. What do we have? Fluorine. We have ortho alkyl product and para alkyl product also formation takes place. Okay. This para one is major again. Okay, this is again major one. Okay, let us go with the acylation. Let us take the chlorobenzene again here. Chlorobenzene with acyl group. Okay, that is CH3 C double bond O Cl. Okay, like I am taking acid chloride in presence of AlCl3 again Lewis base. What happens? This group gets out and formation of acyl carbocation takes place. CH3 C double bond O positive charge. Okay, again the positive charge go to the ortho and para position. We'll get two products over there. Okay, we have ortho product Cl C double bond O CH3, and we have another product, that is para product Cl C double bond O CH3. Again, para one is the major one. Why para one is major one? In the sense, while electrophile comes over there, right, nearing to this ortho position, due to this van der Waals repulsion, steric repulsions, what happens? It restricts to come here over there. That's why it can directly comes over there and approaches at the para position, because of which in all the cases para one is the major one. In certain cases, exceptions are there where the hydrogen bonding formation takes place at ortho position. Okay, remember these conditions. Okay, finally let us see reaction with metals. Okay, we have three reactions over there. One is what? Let us take aryl halide. Okay, let us take X with magnesium, as we have already discussed. Okay, in presence of dry ether, it gives what? It gives aryl magnesium halide. Again, it is Grignard reagent. We have already discussed. Grignard reagent we have already discussed over there. Okay, this is the first one. Okay, let us take the second one. Wurtz-Fittig reaction. What is Wurtz-Fittig reaction? We have already discussed in the case of Wurtz reaction. There is a new bond formation takes place between carbon and carbon. But here, whenever Wurtz reaction is there, we will just take simple alkyl group, okay, RX group. It might be methyl chloride, like ethyl chloride, propyl chloride, like that. Along with this, we will take 2 moles of Na, as we have already discussed in that case. And we have a Fittig reaction, right? Fittig reaction means what? We will take aryl halide. Let us take benzene. To the benzene, we will take chlorine here. Okay. Let me take alkyl chloride here again. Okay, alkyl chloride. Okay, what happens? NaCl gets out over there. Formation of new bond takes place between R and benzene over there. Then what happens with there? We'll get a new bond between benzene and the alkyl group, and 2 moles of NaCl gets out. 2 moles of NaCl gets out. It takes place in presence of dry ether. Okay. Let us take the third one, the Fittig reaction. In the case of Fittig reaction, what happens? We'll take 2 moles of aryl halides over there. Okay. Let us take one aryl halide here, Cl, with 2 moles of Na, and what happens? Another mole of chlorobenzene. Let us take. Okay. What happens again? Elimination of these things takes place. in presence of dry ether, what happens? Biphenyl formation takes place. Biphenyl formation takes place, okay, by the followed by the formation of NaCl over there, okay. In which of the reaction formation of biphenyl takes place means what we have to remember? Fittig reaction we have to remember. In which case alkyl aryl takes place, okay, means like alkylation of benzene takes place means what you have to take? Wurtz-Fittig reaction. In which case higher alkanes formation takes place means what you have to remember? Wurtz reaction, okay. These are all the reaction with metals over there. Reaction with metals over there, okay. Let us take this few questions here, okay. In which alkyl halide from the following page would you expect to react more rapidly by an SN2 mechanism? Explain your answer, okay. Why it is so? In the case of SN2 reaction, always remember primary is greater than, secondary is greater than tertiary in terms of reactivity. We have already discussed, right? We have a primary one and we have a secondary one here, okay. Which one will readily undergo SN2 reaction? The first one will readily undergo what? The SN2 reaction, okay. Let us take the second one here. This is a secondary bromide, this is a tertiary bromide. We know secondary bromide readily undergoes what? SN2 reactions over there, okay. And if you take this one, this is a primary one, this is also primary one, and we should see the branches over there, okay. Let us take the first carbon, second carbon, third carbon. At the third carbon we have a branch, but at the second carbon itself we have a branch over there, right. As the branches nearing to the carbon where the bromine group is there, what happens is that it creates a kind of steric hindrance over there. The nucleophile cannot approach easily over there. That's what the first one is the answer for this one, okay. First two examples in terms of primary, secondary, tertiary will take. In the third example we can take in terms of steric hindrance, right. Let us go to the next one. In which of the following pairs of halogen compounds which will faster undergoes what? SN1 reaction, okay. Now let us take the reactivity of SN1 reaction, right. Tertiary alkyl halides are more reactive, followed by secondary, followed by primary over there, right. Now what is this one? Actually this is tertiary, this is secondary over there, right. Which will readily undergo SN1 reaction? Tertiary will readily undergo, okay. Then we have a secondary alkyl halides and we have a primary alkyl halides. Which one will readily undergo SN1 reaction means what? Secondary will readily undergo SN1 reaction, okay. Let us take another reaction here. Okay. Now let us write all these products. A, what happens A over there? When alkyl halide reacts with magnesium, what happens? Grignard reagent formation takes place. That is R, that is cyclohexyl, magnesium and bromide. Let us take the B over there, okay. Now what do we have? We have alkyl magnesium bromide, right? Magnesium, since it is a metal, it gets a positive charge. The adjacent carbon gets what? Negative charge. If you do hydrolysis, from the hydrolysis, right, positive part comes H plus and OH minus comes out over there, right. Now this H plus comes to the negative charge over there. What is the negative charge over there? Carbon is the negative charge. No, the B is nothing but cyclohexane. At the negative part, hydrogen comes over there. Formation of cyclohexane takes place, followed by the formation of MgOH and X. B is what? Cyclohexane. Okay. Let us take the C over there. Okay. RBr Mg in presence of dry ether. What? It is also again what? What I can say? Formation of Grignard reagent only. What Grignard reagent is this? Like see here, when we do the hydrolysis over there, we got this one, right? From cyclohexyl over there. Because we have cyclohexyl, we got this one. At this point where the hydrogen is connected, magnesium was there, right? Now again we have hydrolysis, but we are not taking H2O, but D2O we are taking. From D2O what will come? D plus and OD minus will come, right? D plus means what? Here the D plus is there. Means in this place the negative charge should be there, right? What is the negative charge over there? That is CH3, CH and CH3, okay? It should be negative. To keep this one as negative, magnesium should be connected, bromine should be there over there, and here what should be the R group over there? R group is nothing but CH3, CH and CHBr and CH3, okay? This is what the alkyl group over there, okay? What is the C over there then? C is what? C is what over there? That is isopropyl magnesium bromide, that is CH3, CH3 magnesium bromide, okay? Because this carbon is connected to the carbon, it's like magnesium, since metals are electropositive in nature, gets positive charge. Carbons are electronegative, that's what gets negative charge over here. Okay, next let us take this one over there, this one over there. Okay, now we have to identify what is D and E. What is D and E? Now we have a particular alkyl halides in presence of sodium in presence of dry ether over there, gives this particular product. This reaction is nothing but Wurtz reaction. Wurtz reaction. We have already done how the Wurtz reaction takes place. Between two R's, new bond formation takes place, right? Like Wurtz reaction gives symmetrical alkenes because the same number of alkyl groups comes from the both side and joins over there, right? Now if we take it is a symmetrical, this is the one where we can separate into two equal halves, right? This is one alkyl group, this is another alkyl group. Okay, let us take R group. What is the R group over there? Isobutyl group, that is CH3, C, CH3 and CH3. Okay, now to this what is connected over there? R X group is connected. Okay, this is the X group. When we take 2 moles of isobutyl group with the sodium, right, we will get what? This product over there. This product over there. Okay. Now, what is the D over there? If we take this one, what should be the D over there? By reacting this one with the magnesium in presence of dry ether, it will give us a Grignard reagent called, that is D, right? Let me take D. That is CH3, C, CH3 and CH3. In presence of X, right? In the place of X, what will come? Mg will come. Next, X will come. X will come. Okay. If we do hydrolysis, what happens? Hydrolysis, what happens? H plus from this one comes to the carbon over here. Then what will get over there? We will get E as CH3 CH, okay, and CH3 and CH3. This is what the E is over there. Okay. Now, how did we get this product? In the sense we got the magnesium Grignard reagent from the alkyl halide, right? How we have got this alkyl halide means from the Wurtz reaction from the product over there. From this we have got Grignard reagent. This Grignard reagent on hydrolysis gives what? An alkene. That alkene is nothing but what? True methyl propane or isobutane. Isobutane over here. Okay. And let us see the next. Yeah, this is what all about haloalkanes and haloarenes. Preparation properties, chemical properties and physical properties and different questions and MCQs, right? We have already discussed how everything has been taking place with all these regions. Okay. This is what all about complete chapter of haloalkanes and haloarenes. You just go through the video and note down each and every point, and when we give the MCQs, right, pause the videos and try to do by your own. If you won't do, just see the video and try to do by your own. Note down all the regions which for all the questions which we have discussed, the stability and the reactivity and all those things. Okay, remaining things we will discuss in the next class and the next video. Thank you for watching.